Let's continue with intermolecular forces. Now we're going to talk about dipole-dipole forces. Molecules such as formaldehyde are polar and therefore have a permanent dipole. The positive end of a polar molecule is attracted to the negative end of its neighbor, giving rise to the dipole-dipole force. So we've drawn the Lewis structure of this a few times. It's actually trigonal in shape because the steric number is 3. These are slightly polar bonds going this way. So the parts that point towards each other cancel and the parts that point up add up. And then between carbon and oxygen is more electronegative. So it's more positive down here and more negative up here. So we have a permanent dipole moment that runs up through this molecule. So then if you put the tail of this one next to the head of the other one, there's going to be that partial negative charge here and a partial positive charge here, and they're going to be attracted to each other. And that attraction is the intermolecular force. And that makes them stick together more strongly than with that dispersion force, because these are permanent dipole moments rather than induced or temporary dipole moments. So let's compare dipole-dipole to dispersion and how that affects the boiling point. So even if you have a similar molar mass but different intermolecular forces, dipole-dipole leads to higher melting point and boiling point. So here we have formaldehyde, which has a permanent dipole moment, and here we have ethane, which is nonpolar. They're very close in size, so just by size, if they only had dispersion forces, the boiling points would be similar. But you can see here, this one has a much higher boiling point and melting point than this one, simply because of that dipole-dipole interactions that the molecules have with each other. So induced dipoles are weaker than dipole-dipole, but stronger than dispersion. So induced dipoles is what happens if you have a polar molecule next to a nonpolar molecule. The proximity of the polar molecule causes dipole-induced dipole. So what that means is this negative part of the water molecule kind of forces the electrons away on this side of the oxygen, creating a dipole in the oxygen. And so this dipole-induced dipole interaction is a little bit stronger than dispersion, but not as strong as a dipole-dipole interaction. The next type of polar intermolecular force we have is hydrogen bonding, sometimes written like this, H bonding. So hydrogen bonding is a super strong dipole-dipole. So it is an example of a dipole-dipole, but it's so strong that it has its own category. This is the strongest dipole-dipole interaction. It occurs between a hydrogen atom bonded to a small, highly electronegative element, either fluorine, oxygen, or nitrogen, and an atom of fluorine, oxygen, or nitrogen in the adjacent molecule. So I like to remember this as phone, so I can remember which three. Phone, F-O-N. So the hydrogen atom has to be covalently bound to one of these elements for it to be hydrogen bonding. So here you can see we have HF. This is a hydrogen bonding interaction here. Between these two water molecules, the interaction between the oxygen and the hydrogen, that's considered the hydrogen bond. So this bond within the molecule is your covalent bond. That's not the hydrogen bond. It's the intermolecular force that the hydrogen bond is. So it's not an actual bond. Then we have down here ammonia, NH3. So when the nitrogen is interacting with the positive, partially positive hydrogen end of another ammonia, that's an example of hydrogen bonding. Now this hydrogen bonding is stronger than the other dipole-dipole interactions. It's not an actual bond, even though it has the word bond in there. Those electrons are not being shared. They're just really attracted to each other because they have a strong dipole moment. So here are some more examples of hydrogen bonding. Right here is acetic acid. And then you can see if you have another acetic acid in solution. So the OH here is covalently bound. And then it's interacting with an oxygen on another molecule. And that right there is your hydrogen bond. Again here, this OH is covalently bound. And that hydrogen is interacting with an oxygen on another molecule. So that's your hydrogen bonding. This is just a network of ammonia. So right here, these are our covalent bonds, the NH3, and then these little dotted lines in here are the hydrogen bonding intermolecular forces. In HF, the hydrogen on each molecule is strongly attracted to the fluorine on its neighbor. So right here, remember we have a big electronegativity difference between fluorine and hydrogen. So we have an overall dipole moment pointing to the right in each of these. So then the negative end here is attracted to the positive end here, and this interaction in here is our hydrogen bond. Another important and relevant example of hydrogen bonding is in our DNA. So you know DNA has to be kind of zipped up and unzipped to duplicate. So it's a little bit easier to break an intermolecular force than it is to actually break bonds. But we also don't want the DNA just falling apart. So hydrogen bonding is what holds the DNA together between those complementary strands. So adenine and thymine form two hydrogen bonds. Right here you can see this N is covalently bound to this H, so NH, and then the hydrogen bonding is happening with the oxygen of a neighboring molecule. Same here, we have this covalent bond between the N and the H, and then the hydrogen bond between the H and the N of the neighboring molecule. Then guanine and cytosine form three hydrogen bonds. So you can see there's one here, here, and here. And it's those hydrogen bonds that are holding the DNA together. Hydrogen bonding is also the strongest intermolecular force in water. Water molecules form strong hydrogen bonds with one another. The boiling point of water, which is 100 degrees Celsius, is really high for a molecule that has such a low molar mass. So if you think it's only 18 grams per mole, that's pretty small. But they're held very strongly together because of that hydrogen bonding between the water molecules. So those water molecules are really attracted to each other. So it takes a lot of energy to separate them from each other. So let's look at the effects of hydrogen bonding on melting and boiling points. So even if you have similar molar mass, but different intermolecular forces, hydrogen bonding has much higher melting point, boiling point, compared with dispersion forces. So if we look at methanol, you can see this OH here. So when this hydrogen gets close to an oxygen of another methanol, you're going to have that hydrogen bonding. Ethane, you can see, is nonpolar. So you can see the boiling point for methanol is a lot higher, even though they're very similar in size. Now let's take a look at boiling points of binary hydrides, which basically just means you have hydrogen bound to one other element. So the boiling points are related to those attractive forces, those intermolecular forces. You have increased boiling points of water, HF, and NH3 are due to hydrogen bonding. So you can see it mostly follows this kind of upward trend. But these outliers here, with really high boiling points for how small they are, is because of that hydrogen bonding. And remember, that's when you have that H covalently bound to an F, O, or N phone. So now I want you to practice what you've just learned. Identify compounds with hydrogen bonding. Circle the compounds that exhibit hydrogen bonding. For the ones that do, circle the area of the compound responsible for that hydrogen bonding. So I want to make sure that you can identify which ones have hydrogen bonding and which ones don't. So go ahead and pause the video and take a second to answer these questions. All right, let's go through these examples and see if you got the right answers. All right, so this compound has hydrogen bonding. Let's look at the first one. So the first one, even though there's a hydrogen and an oxygen present, they are not covalently bound to each other. So this is not an example of hydrogen bonding. This is just dipole-dipole. This one does have hydrogen bonding, so let's see if we can find the region of the molecule responsible for the hydrogen bonding. Right here we have an oxygen covalently bound to a hydrogen. So then when that interacts with, say, when this hydrogen interacts with, say, this oxygen from another one of these, you're going to have your hydrogen bonding. Or even if it's interacting with this oxygen over here. All right, let's take a look at number 3. Do we have hydrogen bonding here? Yes or no? Yes, we do. And it's because we have this nitrogen covalently bound to a hydrogen. And I put these different types of drawings just so you could practice looking at these some more. Remember that these represent carbons, which are saturated with hydrogens. So right here you have a carbon and 2 hydrogens. Right here a carbon with 3 hydrogens around it. All right, now let's take a look at number 4. Does this one have hydrogen bonding? No, because even though we have nitrogens and hydrogens in this compound, the nitrogens and the hydrogens are not covalently bound to each other. This nitrogen is bound to 3 carbon atoms, and then it has 1 lone pair. So it is not covalently bound directly to a hydrogen, so there's no hydrogen bonding here. And then let's take a look at this last one. Do we have any hydrogen bonding here? So even though we have fluorine and hydrogen in this compound, the fluorine, sorry, I forgot to click that. The fluorine is not directly bound to one of the hydrogens, so this does not have any hydrogen bonding in it. All right, now let's take a look at the last force that we're going to talk about, which is ion-dipole forces. So an ion-dipole interaction is the attractive force between an ion and a molecule that has a permanent dipole. So for example, here you have a sodium ion and it's surrounded by water molecules. This happens a lot if you have salts dissolving in water. So you get a sphere of hydration, which means a cluster of water molecules surrounding an ion in aqueous solution. Typically it's water, right? We've talked a lot about water in chemistry because that's what's in our bodies and that's our most common solvent is the water. We call it that sphere of hydration. But if it's something other than water, you call it a sphere of solvation, if the solvent's something other than water. But we're mostly going to be looking at examples with water. Here's an example of an ion-dipole. Ion-dipole forces exist between sodium and the negative ends of water molecules, and between chloride and the positive ends of water molecules. So if we look at the chloride first, this is our negative anion of chlorine, and you can see that these water molecules have their dipole moments pointing away, which means the positive end is surrounding the chloride ion. For the sodium, it's exactly opposite. The water molecules flip around the other way, so that the partially negative end is close to the positive cation. And then they form this sphere of hydration around each ion. And that's what happens when salt dissolves in water. So here's just another look at our ion-dipole sphere of hydration. So this is your solid sodium chloride before you decide to dissolve it. Then you put it in the water, and the water molecules start surrounding this and taking off the sodiums and the chlorides one by one until it dissolves. And this is what a bigger sphere of hydration looks like. So the one we looked at before, this is just the water that's surrounding the ion, and then you have another layer of water around that and another layer around that. That is then into your bulk water. So right here, this is our chloride ion, and between those water molecules, that's our ion-dipole interaction. But then when you're looking just from water to water, that's a dipole-dipole interaction. So if you're looking at salt water and you want to identify which intermolecular forces are present, right around the ion, you're going to have those ion-dipole interactions. But then once you get into the bulk water, you have that dipole-dipole interaction, which is actually hydrogen bonding, which is a type of dipole-dipole. So how does a solid dissolve in water? You have this competition going on. So the solvent-solute attractions overcome the solute-solute and the solvent-solvent attractions. And remember, the solvent is the thing you have the most of, and the solute is the thing you have the least of in a solution or a homogeneous mixture. So there's kind of this competition happening between all of these to see whether it's going to dissolve or not. The positive ends of the water dipoles are attracted to the negatively charged ions, and the negative ends of the water dipoles are attracted to the positively charged ions. So here's the summary of our intermolecular forces, from weakest to strongest. So first we discussed the dispersion force, and that's what non-polar molecules have, and it arises from instantaneous dipoles. Then all the rest of these are for polar molecules. So dipole-dipole, these are your polar molecules where the positive and negative ends of dipole moments are interacting with each other. Then hydrogen bonding, polar molecules containing a hydrogen bonded to a fluorine, oxygen, or nitrogen. And then you have the ion-dipole, where you have an ion and a polar molecule. So at this point, I would want to be able to give you a compound, and you would tell me which intermolecular forces are present, and maybe be able to arrange them in a predicted order of boiling point or melting point based on those intermolecular forces. So here's just an image with a summary of those intermolecular forces. So we have the strongest one being the ion-dipole, then hydrogen bonding, dipole-dipole, dipole-induced dipole, and dispersion. And remember the ones, if you're trying to find which has the highest boiling point, it would be the one with the stronger intermolecular force. So just a quick review to make sure everyone is really paying attention and understanding the concepts. What's stronger, intramolecular or intermolecular forces? So remember, intramolecular, those are those covalent bonds, and intermolecular is the interaction between molecules. So recall that intramolecular forces are much, much stronger than intermolecular forces. Because when we boil something, we're breaking the molecules apart from each other, but we're not blowing the molecules up and stripping them of their atoms, right? The molecule itself stays together. So now I want you to practice identifying some intermolecular forces. So take a second, pause the video, and see if you can predict the intermolecular forces present here. And remember, there can be more than one. All right, so go ahead and start the video back when you have completed these questions. So HCl, the chlorine is much more electronegative than the hydrogen, so you have that permanent dipole moment there. So you're going to get dipole-dipole and dispersion. Remember, dispersion is always present. HF, you have hydrogen bonding because that H is covalently bound to an F. You have dipole-dipole and dispersion. Then what about hydrogen? Hydrogen is non-polar, so you have dispersion only. Now let's take a look at number 4, carbon monoxide. The oxygen is more electronegative than the carbon, so you have an overall dipole moment. So the intermolecular forces present here are dipole-dipole and dispersion. So remember, when you're going to predict boiling points, you're going to go by the strongest one present. So that's this first one I have listed is the strongest one. So that's the one that's most important to identify and use to say which one's going to have a higher or lower boiling point. All right, now let's take a look at potassium chloride, aqueous. So that means it's dissolved in water. So you're going to have your ion-dipole, just for the KCl, and dispersion. Then for methanol here, this O is covalently bound to this hydrogen, so you have hydrogen bonding, dipole-dipole, and dispersion. And number 7, H2S. You might have to draw out a Lewis structure for this one. So if you draw out that Lewis structure, you're going to see that it's bent, and you have an overall dipole moment pointing kind of in the direction of the sulfur. So you have dipole-dipole and dispersion. So make sure you practice identifying these intermolecular forces for different compounds so that you can get really good at it and really quick at it and knowing which one's strongest. So let's take it a step further and predict boiling points. Let's rank the following compounds in order of increasing boiling point. All right, so here this oxygen is attached to this hydrogen. Here you just have a carbon chain. And for this last one, this oxygen is actually attached to this carbon and this carbon, so it's not directly bound to the hydrogens. If you need to, you can Google these so you can look at the structures. Okay, so let's take a minute, pause the video, and see if you can rank these in increasing boiling point order. So the lowest one is going to be the one that just has this carbon chain because this is all non-polar. The only forces involved are the weak dispersion forces. Then the next one is going to be this one where you have the carbon bound to the oxygen, bound to the carbon. So it has a similar molar mass, but it also contains dispersion and dipole-dipole forces because of that oxygen. The last one, this oxygen is covalently bound to the hydrogen. So here you have hydrogen bonding. So even though this guy's smaller than the other ones, about half the size, it has that hydrogen bonding, which is the strongest of all the molecular forces. So it's going to have the highest boiling point. So now you can use what you've learned about drawing Lewis structures, predicting that three-dimensional shape, using that delta En, or what you know about electronegativity differences to figure out the direction of the dipole moments of the bonds and the dipole moment overall for the molecule. And then you'll be able to figure out which intermolecular forces are present, and then you can figure out which one is going to have the highest boiling point. So take some time and practice those.